Okay. So this is ongoing work with Chris. Gosh, how many years has it been? Assessing disclosure risk in microdata. And we recently started some new work, but unfortunately I can't come to you and say we solved it all and it's all done. So it's very much work in progress that I thought I'd tell you about. But the idea is to sort of tell the story, how we actually started back in the days, what was it, 2005, 6? Where we started looking at the disclosure risk assessment for identity disclosure in microdata. So here the assumption is it's microdata. We're worried about re-identification on a set of quasi-identifiers. We've heard over the number of the last days that sometimes people link the masked data to the original data and try and get a probability of a correct link. Well, I always thought that wasn't a very good idea because there are properties, certainly in sample microdata, where it certainly would overrepresent the disclosure risk because number one, the intruder would probably not have the original data. Number two, it doesn't take into account the sample fraction, and the sampling obviously gives a lot of protection in the microdata. And we're talking about the types of microdata in this first setting where, like the labor force survey or these social surveys that are conducted by the agencies, they have very small sample fractions. They're usually deposited in an archive, and researchers can get access to the microdata. So the way we approached assessing disclosure risk for this identity disclosure risk for these types of sample microdata was through a probabilistic modeling, which I'll just briefly mention again. What the models are, and then we subsequently extended that to the case of perturbation, misclassification of perturbation, because we all know that sample data is very messy and there's a lot of errors in the data, and there are certainly errors in the data when we on purpose perturb the data. So how do we measure disclosure risk in that setting? And then the new work that we started extending to subpopulation microdata. So as I said, the notion of identity disclosure about the possibility to link, an intruder might have a publicly available data and they'll link to the microdata on a set of quasi-identifiers, and then of course microdata's got loads of other variables, and then we end up with active disclosure. So in the probabilistic modeling framework, we have a sort of a Q-wave frequency table, which is represented by these quasi-identifiers. Obviously, there's no names and addresses on the file, but the quasi-identifiers are typically categorical, so there's sex, age, race, the sort of thing we saw on Mark's slide. And we can produce a frequency table and put the counts in this table. So little fk is the sample counts, and the capital Fk are the population counts. So, if we knew what the population counts were, we'd obviously see right away on a sample count of, 1, is this particular cell risky? Is there a 1 in the population, or 2 or 3? But the issue, and of course we can derive our disclosure risk measures. So in the classical setting, Sylvia's worked a lot on this stuff as well. The tau 1 is simply the number of sample uniques that are population uniques, and the second one is actually the matching probability, 1 over the population count. Now we are focusing only on a very small part of this distribution, which are the 1s, right? Because if I observe 2 or 3 in the sample microdata, and I'm talking about sample fractions that are 1 in 400, 1 in 500, 1, very typical, certainly in the UK, then, if I'm observing 2, that there's got to be at least 500, 600 people in the population. So we really only focus on the sample uniques because those have the potential to be a population unique. So it's really quite straightforward. I don't know the population counts. First of all, you should know that the samples are typically drawn from address frames, so we don't know the population. Maybe we know every 10-something years if there's a census. But we don't know them, and so typically we need to estimate these population counts. Or as you've seen earlier in talks, the scenario where I've got my original data set and I can link it back. But you have to have some sort of, assuming some sort of population-based data set that I can use to attack this microdata. So we're going to try and estimate this match probability using the probabilistic modeling. So in order to use the probabilistic models and to estimate my risk measures, tau 1 and tau 2, I need to know, based on these distributional assumptions, what the probability is of a population unique given a sample unique, and what is the expected value for the match probability. Now, a very natural assumption in contingency tables, which does, bring in mind Steve Feinberg and the lessons I've learned from him. Of course, we always assume sort of multinomial distributions in contingency table literature. In this case, we're only interested in the one, right, that population unique. So we're going to assume a natural assumption that the population count is distributed Poisson with a lambda k. We're assuming that we have a simple random sample or Bernoulli sampling within a k, and you'll see that most of our examples, I'm assuming that you have equal selection probabilities in our surveys, which is typically what happens in the large-scale government surveys, because they might have quite complex designs, but at the end of the day, they have an equal inclusion probability. So we're assuming Bernoulli sampling within a cell, pi k, taken from the population count, capital F k, and I'm going to be sort of getting rid of that k, just assuming equal probabilities. And then it follows, of course, that a thinned Poisson distributed random variables also Poisson distributed now with a pi k lambda k. The pi k is the sample fraction. And if you do the algebra, then you can get the conditional distribution of population count fk given the sample count little fk is also Poisson distributed. Everything's really easy, really simple algebra. And in this case, the parameter now is lambda k times 1 minus pi k. So everything's really easy, and it's a Poisson distribution, so those probability of a unique, population unique, given a sample, it's all very easy to calculate those measures. The problem is, how do we get these population parameters, in this case the lambda k? And of course, the earlier work by Chris used log linear models to estimate these parameters. Because we know that the sample frequencies are also Poisson distributed with a mu k of pi, that is equal to pi k lambda k, run the log linear model, solve the score functions, and we get the estimates for the mu k, and then we simply divide the estimates of the expected cell counts from the sample, the mu k, by the pi k to get an estimate of the lambda k. So it's all, so far, still, really year one statistics, all really easy. Again, we know that the conditional distribution of the population given the sample counts is Poisson, so we can develop our probability of the population count is equal to 1 given the sample count is equal to 1 is simply the exponential of the parameter. And then we, a little bit more algebra, we can get the expectation of 1 over fk, and we end up with an expression like that. So it's all simple, right? All we need to do is run a log linear model, take these parameters, put them in the forms there, and we're done. Well, the problem is that when we're looking at, if you remember your year one statistics, and maybe Steve Feinberg taught you, we learned that to do a goodness of fit criteria to select the log linear model, we had to have a expected cell count of at least 5. I think that was it, right? So what happens with these tables is we have sample counts. They're really, really sparse, and the tables are just huge. We're talking about very big contingency tables multiplying all the quasi-identifiers. So you can imagine they're very big, and you'll see in my example. And so these assumptions in log linear model, I can't use the standard deviance or chi-square statistic to select which model to use. And this paper that we did in 2008 actually developed goodness of fit criteria to select the model which will give me unbiased disclosure risk measures. And it's interesting that these goodness of fit criteria is actually based on the notion of over or under dispersion, because the Poisson distribution assumes equal variance to the expectation. So when do the assumptions of the Poisson distribution hold? When we need to have some sort of indication of when we have over or under dispersed models. So the issue with the overfitting, for example, using the Bishop Feinberg book, what is the third author? Can't remember. Yeah. You can do some sort of iterative proportional fitting to these sample counts, say you've got two-way interactions or three interactions. You can do some iterative proportional fitting to get your mu k's, subsequently get the lambda k's to plug into your formula. And what happens if you have too many interactions, think of these margins that we're fitting, there's too many zeros on these margins, and we have too many cells that we're estimating to be zero. And so basically the non-zero cells are going to be too large, and what's going to happen to our disclosure risk? It's going to go down. So we found that there's a monotonic property in these models. So if I had done an independent model, I would have absolutely no zeros on the margins. All the cells would be attributed some sort of mass to the population, no zeros, and then the ones that I'm worried about, the population uniques, they're going to have a count that's too small, and what's happening to the risk? It's going to go up. So there was a monotonic property that we saw in these sort of models, and so we developed the criteria to find when are the risk measures unbiased. And the idea is to start with a forward search on sort of the independent model, and then gradually add in interactions until we meet the criteria, which is normally distributed. So anytime we get to 2, we're happy we found the right model. It's got the correct dispersion, the estimate. I can estimate the parameters, put them into those formulas, and there we go. So just a quick example: a population about 1 million from the UK census, 1 in 100 sample here. These are the keys. I had 2 areas in this data set. Gender is 2, age, there were individual ages, 101 ages, marital status, etc. 412,000 cells in this particular contingency table of a sample size of 9,448. So you can really see how impossible it is to try and fit models on these types of tables. So again, we start with the main effects, gradually adding interactions until our goodness of fit criteria tells me I can stop. And well, I didn't explain it too much, but it's based on the issue of when the mean is equal to the expected mean, and the variance is equal to what I expect. So it's kind of based on the notion of whether I'm got the correct dispersion, the over and under dispersion problem solved. So if I look at the independent model, and I have my expressions for the goodness of fit, you can see that again in the independent model they are too high. Oh, I should mention the truth. Right? This is data that I used from the census, so I do know the truth. The number of population uniques that are sample uniques was 159, and then the expected number of correct matches is 355.9. So if I have a myself and there's nobody else like me, I'd have 1 over 1, that's a 1. If there's 2 like me, 1/2, 1/3, and I just aggregate. So that's expected number of correct matches if within a group I allow sort of random guessing. But anyways, you can see on the independent model, I'm far too high. You can see the risk measures are also very large. If I look at the all two-way interaction model, I'm getting just a little bit too low on the risk measures. You can see they're not within my interval of plus minus 2. And I can start gradually entering interactions, 1, 2, 3, 4. You can see already at model 4, I can certainly stop. I could have stopped at model 3. But you see that I'm very close to the global measure of 159. And in fact, I simply went on in this chart to show you how, that there's a sensitivity here. I'm pretty much in the range no matter where I stop, but as long as my global risk, my global criteria are telling me that I can stop. So that's the idea for the model search. And if I look at the individual, what's really nice about this theory is that the individual risk measures compose the global measures. So I can take the individual risk measures, aggregate them, I get a global measure, and this is what the microdata review panels want to look at. They want to see a microdata, and we can say, look, you've got a 2%, 3%, 4% re-identification. They can go back and say that's fine. You can pass it on to the archive. Otherwise, go back and do something else to the data. And in this sense, we can look at the individual risk measures and see, well, where should we do some more recoding or some more coarsening to bring that disclosure risk down. Now, what you see in this is the individual points for these sample uniques. And it's on a log scale, so it looks kind of funny, but this pink line is the correct true risk measure versus the estimated risk measure from this log linear model. And what you can see that the global measures are very nicely, can be accurately estimated based on this method. I'm not doing too well at the individual level, which is okay, because if I can do that, so can the intruder. So, but you can see that at the in expectation, we can do pretty well with these two measures. Now, we're looking at this method, but in fact, there are some countries that do perturbative methods. Usually, in many countries, they won't perturb their sample data because it goes into an archive and there's some protection. They'll do some subsampling or recoding or collapsing of key variables or deleting, lower level geographies. But in some cases, you might see perturbative methods like data swapping or adding noise, misclassification. How do we then go about and assess the disclosure risk? And the idea there is that if we can, any type of perturbative method, if we can put that in a sort of a misclassification framework, a measurement error framework, we can deal with that in the risk assessment. So if we define an MKJ, the probability that the category was originally J has now turned to originally K because I did some post-randomization method, and I can define this sort of probability or perturbation mechanism. I can try and incorporate that into the models. And in fact, in the paper in 2010, we did just that. We incorporated the measurement error model into the risk, the matching probability framework. You can see the expression there in 1. Now what happens is that if we are doing any perturbation or misclassification like post-randomization method, it's very, very small. I think Mark mentioned 0 to 5%. The 0%, by the way, in the census was because they didn't do any perturbing if they had an area that was mostly imputed. So there's a lot of imputations going on in the census. So anyway, so if we have very small misclassification and very small sampling fractions, the expression 1 will reduce to expression 2, which is very simple. All I need to do now is to use the framework that we used in the original case, but instead of using my sample data, I need to use my perturbed sample data because I need to estimate the population counts from as if the perturbed data was generated if the population was generated from that perturbed sample. And we can try and use the same sort of setup on the perturbed sample to generate perturbed population counts and get an idea of what the global measures are in that sense. So again, I've got a census data, 1,000, no, this time I had 1.5 million. 1% simple random sample, 14,683, very big key. Over 500,000 on the key for the sample size of 14,683. I did record swapping and I did the post-randomization mechanism, and I put it into this framework of the M probability matrix. In this case, I did a 20%. By the way, nobody's doing 20%, so this is very extreme, so you don't have to worry about what you're seeing here. But anyways, it was 80%. We didn't touch any of this. We didn't do any swapping for 80%, but on a random sample of 20%, we swapped them around. And same for post-randomization method. It's just a more general method of doing record swapping. So based on these methods, if I was just doing naively, not thinking that I perturbed the data set at all, the true measure would be 358.1 expected matches and 362 for the swapping. They're very similar. They're actually pretty much similar mechanisms. And I know how to estimate the risk for that, assuming naively that we had done nothing to the file, and I get a good measure of the global measure, as we saw in the previous example. But of course, the true risk measure is actually 292, because I'm only going to do the risk measure on records that I didn't touch. So the risk measure on the non-perturbed records is 292 expected matches. And if I use the mechanisms of the formula that I showed before, you can see that also on average, I get a pretty good estimate of the risk measure, and also based on the estimated risk measure using the log linear model on the perturbed sample counts, I get a pretty good global measure, and again, you can see on the diagonal, I've got the true risk measure on the y-axis, the estimated risk measure, using the log linear model on the perturbed sample to get an estimate of the disclosure risk. So the new work, all that just to tell you about the new work, is that up to now the sample has been a random subset of the population, right? And intruder knows that the individual in this data set can be linked. And the new problem that we're dealing with now is that the microdata contains members of a subpopulation where the membership is not known. And a good example would be all persons with a medical condition, like in a cancer registry. So it could be a whole population of, cancer patients, or maybe a sample of cancer patients, but the membership is not known, and the membership is sensitive. So the subpopulation now is not like a random sample. I can't infer from the subpopulation what my population counts are. But again, we're still assuming that the attack identity disclosure, that an intruder would be able to match the subpopulation to an individual, the population, where the subpopulation is definitely a subset of the population. And again, we're not dealing with measurement errors yet. So the idea is to use the sample microdata to make inference about the population uniqueness in the subpopulation. So we're going to try and use the random sample to infer the population parameters based on assessing the disclosure risk of this subpopulation, which is not generally representative. Okay, so since I haven't finished the work, 5 minutes is enough. So we're assuming that the population counts are not known again. We're assuming a simple random sample, little fk again is the sample frequency in cell k. Now the tags, fk tag is the population count in the subpopulation. And maybe we took a sample from the subpopulation with an fk tag, so all the tags are the subpopulation. The two scenarios here, disclosure risk and subpopulation, similar to what we saw previously, the tau 1 star. Given it's a subpopulation unique, what is the probability that it's a population unique? And also, if we had a sample from the subpopulation, we'll leave that for now. Again, is it a population unique? So the idea is, again, following from the earlier work, the population counts are Poisson distributed with the lambda k. But now we've got a new problem here, right? We've got within each cell k, we have a random variable y, which takes the value 1 with the probability pk independently for each of the fk units, so that fk is Poisson distributed with the psi, but the psi is based on this propensity pk. So the new parameter I need to worry about, this psi k, is lambda k times pk. So I have now not only lambda k's I have to worry about, I also have to worry about the propensities, the pk, and that the fk tag, the subpopulation counts are binomially distributed with the population fk and this propensity, this pk, that needs to be estimated. We're assuming that the pk follows a logistic model, as often is done, with a new set of parameters on the psi there, xk tag psi. Again, we're assuming that the simple random sampling, as we've seen before, for the population, for the sample counts, and again, the sample counts are Poisson distributed. And then I can come up with my risk. The measures is simply exponential of minus lambda k minus psi k, and of course, if I had a sample, it would be pi k psi, tag times the. I'm probably not saying this is psi k. What are those? Phi k. Sorry. Anyway, so the idea is that we started with a two-step approach. Let's estimate the population parameters, as we've always done, with using the sample counts, and then fix those. And then given, fixing these lambda k's, now let's estimate the phi k, not psi k, phi k based on the psi's, using, the likelihoods of the logistic regression, method of scoring. It's all got quite complex. But we thought we'd try it in a two-step approach. And just to show you what happened in that sense, I had, again, I keep having a different number of UK census numbers. But the subpopulation in this case were those with long-term illness. So you can imagine that they're probably elderly people, you know, long-term illness. Again, I've got the sample. I did a 1 in 50 random sample to infer on the gammas, and I've got different sizes of the sample counts for the subpopulation, plus, of course, the subpopulation itself with a sample fraction of 1 in 1. Fix the lambda k, as I saw earlier. Now let's estimate the phi k's and see what we get. Well, we didn't do very well. So, you know, just looking at the whole population count, we did okay. You know, I thought, all right, that's looking good. But the minute I started with the sampling of the subpopulation, you could see that the bias is getting progressively worse. So I'm not able, if I fix the lambda k's, I get a lot of zeros that are estimated. Exponential 0 is a 1. And so I'm getting this ridiculous, you know, overestimation. And just to check that the theory is right, I used a set of the estimates of the lambdas and the phis, and I generated a population, took the random sample. So now, you know, it's not an element of having to estimate these measures, and I could see that, you know, at least we could verify that the theory is right. So the idea, of course, in the future work is to forget about this two-step approach. It's not working. And that we're going to develop a modeling framework for estimating the joint likelihood of both the lambdas and the psi's, probably under an EM algorithm where the missing are those sample units that are actually part of the subpopulation units. So it's a very, very complex model that we need to get into, and then once we sort that out, we'll have to think also about goodness of fit criteria for those types of models.
Okay. Thanks very much, Natalie. Questions?
Just
a question.
Little one. I mean, why not you talk about the EM algorithm there? Can you not try like a Bayesian approach and do like an MCMC type thing and get?
Yeah, I'm sure we are doing that.
Might
there is some sort of MCMC there because it's very tricky.
Well,
you've got two sets of parameters, you know, big vectors, and there's, yeah.
I had suggested sort of incorporating important sampling into the EM algorithm there. But
well, so that's the thing, because you can do like this MCEM, but I think if you're going to do that, you might as well do a full Bayesian thing, because otherwise you're just going to get like a point estimate at the end, right? So, I mean, if you just incorporate the whole thing, you can get a posterior distribution. So, anyways.
But there's two sets of parameters, both the lambda and the phi. So.
Okay, well, we can talk later if you want. It's very interesting, so yeah.
Any other questions?
Okay.
I was looking forward to it. Okay, right. Thank you very much again.